Good morning.
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 All right, folks, it's 8 o'clock. We'll get started here. So today we're going to be talking about Le Chatelier's principle and equilibrium. All right, so let me show you something about the concept of equilibrium. Let me see. Here we go, Introduction to Equilibrium. Now, I'm not going to play the whole thing, obviously. I'm just going to play a little bit of it. Now, I'm going to get smarter about this. I have to share the sound. There we go. Share computer sound. Ha 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 ha. All right.
I'd like to give you an introduction to.
Let's see. Here we go. All right.
And here we've got a reaction where we're going from 2A to B, and the A's are red and the B's are blue. Let's take a look at how the reaction goes. All right, so we're starting off with all reds here, and again the reaction is 2A gives 1 blue. Now what you can see here is we start off with.
Can you all hear the stuff coming out of the video?
Yeah, I can hear the video.
All right, good, good. Thank you.
80 molecules of red, and we start off with 0 molecules of blue. And eventually, as time goes on, the amount of blue evens out at around, looks like about 20, and the amount of reds is going to even out at something like about 50. Now, what's going on here is that the number of reds and blues is now constant, because you can see that we've got roughly parallel lines going on here. Now, what I want you to do is just follow one of these blues and see what happens to it. I'm following this one. And what we're going to see is that at some point this blue is going to switch into 2 reds. So it's going to react. But at the very same instance in the reaction, 2 reds are going to become a blue. So these are not the same reds and blues that we're seeing here. They're reacting and they're changing, but the number of blues and reds is remaining constant, and that's how we're obtaining this equilibrium type situation. This blue doesn't look like it wants to change, but it will change at some point. And you can see all around it, you see reds turning into blues, you see other blues turning into reds as well. There we go, it's gone now. And what happened was it turned into 2 reds, and then somewhere else 2 reds turned into a blue. And it was almost an instantaneous type situation.
All right, so that's equilibrium in a nutshell. So what you can see is at the very beginning, we'll take it back to the very start here.
To look at how the reaction goes. All right, so we're starting off with.
You can see that there were 80 reds and 0 blues. Now I think it was 2A to B is the reaction. So 2 reds give a blue. And then what happened was, of course, the number of reds went down and the number of blues began to go up until they became constant. And that's equilibrium right there, when they become constant. All right, does anybody have any questions? That's really just giving you an introduction to what equilibrium is. It's not a bad little app that was there. I mean, no longer exists, unfortunately, because I think it might have been Flash, and Flash is going the way of the dodo. All right, does anybody have any questions so far? Okay. Just getting my drawing screen ready here. All right. So what we can talk about is K, the equilibrium constant. And the constant part becomes because the products and the reactant concentrations become constant. And this value becomes constant at any given temperature. Now, in any reaction, we can figure out what the equilibrium constant is if we know what the concentrations of the reactants and products happen to be. And in all cases, it's going to be products over reactants, and that's going to be C to the power of little c, which is the coefficient, big D to the power of little d, which is the coefficient, over A to the little a and B to the little b. And these are the concentrations multiplied by the to the power of the coefficients that you see here. Effectively, what we're doing is we have all this stuff here that's been added, and now we're just multiplying it all together to get this equilibrium constant. Does anybody have any questions so far? So K only matters at equilibrium, when those lines were parallel. So here's what we know. If K is greater than 1, then then at equilibrium we have more products and reactants. If K is less than 1, we have more reactants and products at equilibrium. So you can see it's K equals products over reactants. If K is greater than 1, this top number must be bigger. The products are bigger. And if the K is less than 1, then the reactants must be bigger than the products. So that bottom number must be bigger. So this is big K. It's different to little k that we talked about earlier, which was the rate constant. This is called the equilibrium constant. It's a big K. I didn't check here. Okay, it's got some people here. It's good. Now, the thing is that reactions aren't always at equilibrium, but if they're not at equilibrium, we know at some point they will be. But we need a way to be able to express what's going on when the reaction isn't at equilibrium. Now, if I go back to that video that I showed you earlier, at this point, before we get to these parallel lines,
Before red's here,
and these are sloping towards those parallel lines, it's not at equilibrium yet. That means that I can't use K to get any values at this point because the reaction's not at equilibrium. What I can do, though, is I can use this expression called Q. Now, Q has exactly the same form as K, except now this could be used anytime. It doesn't have to be just used at equilibrium. It can be used anytime, even when the reaction is not at equilibrium. But here's what we know. If Q equals K, then the reaction is at equilibrium. If Q is less than K, the reaction will have to shift towards the products. If Q is greater than K, the reaction will have to shift towards the reactants. All right, so that's when things start to get a little bit more difficult. Let's talk about what's going on with Q and K here. All right, so let me see. I might have I think I do have something later on in the video about that. So let me pull that up here. All right. Did I change this one? Yes, I did. Good. All right. I edited it. All right, so I'm not going to play the video. I'm just going to use bits of the screen for it here. So let's say we've got this situation here where y is going to 2x, and this would be the situation at equilibrium. So remember, at equilibrium, the concentrations of x's and y's are not changing, right? But you saw in that video, it's dynamic. The x's are turning into y's, the y's are turning into x's, but it's all happening at the same rate. So we're ending up with constant concentrations of x and y at equilibrium. So then I ask you to entertain two cases here. This one where we have a whole bunch more y, and this one where we have a whole bunch more x's. Now, if I wanted to actually calculate the K value, it's fairly simple. What I do is I take the number of x's squared over the number of y's. Now, by number of x's, I count them up. 1, 2, 3, 4, 5, 6, 7, 8. And the y's, there's 5 of them. 1, 2, 3, 4, 5. And since this is at equilibrium, because I'm telling you it is, then we come up with a value here, and this is going to be our K value, 12.8. Does anybody have any questions? Remember, I'm making this up, right? So let's look at case A, where there's a whole bunch more y's than we had before. And then what I'm calculating here is not Q, sorry, not K, but Q. Now, how do I know that? Well, this is equilibrium. If I'm adding something to it, I'm no longer at equilibrium. So I'm not talking about K anymore, I'm talking about Q. In order to calculate Q, I just count up again the number of x's. Here we've got 4, and the number of y's, we've got 7. So you notice we have 2.28. The whole point of this is that if I have a reaction that's not at equilibrium, it wants to get to equilibrium. So Q is at 2.28, but it wants to be 12.8. I'll say it again. Q is at 2.28, but it wants to be at 12.8. So the question you've got to ask yourself is, well, what's going to have to happen in order for Q to become K? Well, what's going to happen is that the x's are going to have to get bigger and the y's are going to have to get smaller, which means the reaction is going to have to shift towards the product side if Q is less than K. And this is the way it's always going to be. I'll stop right here because I really need to make sure you understand what's going on. Does anybody have any questions? I can't believe nobody has any questions. I'm finding it hard to believe. I mean, I'm good, but I'm not that good, surely. Come on. I'm just kidding. I'm just kidding. Can you all hear me?
Yes.
Thank you. Just making sure I wasn't talking to myself. All right. Let's look at case B here. Now, case B, we have, it looks like a whole lot more x's and a whole lot less y's. So let's take a look at the Q for that one. And you can see that if I count up the x's, it comes out to be 10. So that's 10 squared. And that's going to be 100 divided by 4 on the number of y's, which comes out to be 25. This is more than 12.8. So what that means is that the number for Q needs to go down in order to get to equilibrium. In order to make that number smaller, the number of y's must increase and the number of x's needs to go down. And that's what's going to happen. So this would shift towards the reactant side to produce more y to get to equilibrium. That's really what I want you to understand. So Q is greater than K, the reaction shifts towards the products. If Q is Q is less than K, the reaction shifts towards the products. If Q is greater than K, then the reaction shifts towards the reactants. And that's what I mean by that statement I was making on the PowerPoint slide. Does anybody have any questions about any of that? It's really important you understand it. Because if you understand this, everything else is fairly easy.
So just double checking if Q, the reacting components, is less than K, then I'll shift to the reaction.
No, products.
Yeah, products. And if Q is greater than K, I'll shift to the reactions.
To reactants, yeah, that's right. Yeah, but it's important not to just memorize that. I think it's important to understand the reasoning behind it. And the reasoning is that if a reaction is not at equilibrium, it wants to get to equilibrium. So the Q will always approach K. So wherever Q is, it'll always try and get to K. You'll always know what K is, right? It's not going to be something you have to guess. Right? K is
So-
something you would always have.
So when calculating for K, you keep it the same, but when you calculate for Q, it's going to be different every time.
Well, actually, the X's and Y's, just to be real clear here, Alyssa, the
Yes.
X's and Y's can be different, but for K, they're always going to come out to be 12.8.
Okay.
There's lots of different combinations of X's and Y's that will still give you 12.8.
Okay.
Is that fair enough?
Yep.
Okay. Any other questions? All right. So here's an example, and this is similar to what you'll see in the test questions. So considering the following reaction and data, and I'll give you a reaction, and then I'll give you the K value. So you're given that. You don't have to figure that out. Right? I'll say it again. You're given this K value, this big K value. Now, these are of the concentrations. So the first thing we want to do is look at these concentrations, and we need to determine if the reaction is equilibrium or not. And what we do there is we come up with the Q expression, which is going to be products over reactants. So it's SO3 to the power of 2 over SO2 to the power of 2 times O2. Now I'm going to stop there for a second. Is everybody okay with how I'm coming up with this Q expression? The thing I'm circling right now. Is everybody okay with that? Okay, good. So then what we do is we substitute in all these different values we got here. So just plug and chug at this point. So the 6.9 goes in for the SO3, 6.9 times 10 to the negative 3, 1.9 times 10 to the negative 3 goes for the O2, and the 5.0 times 10 to the negative 3 goes in for the SO2. So we calculate a value here, and this is a Q value, right, that we're talking about, and it comes out to be 1002. When we convert it down for significant figures, 1.0 times 10 to the 3. So we know that reaction is not at equilibrium, and that's because Q does not equal K. We know what K is, it's 279, but Q is actually 1000 or 1002. So that's the first part. Does anybody have any questions about that?
Will we be given like those 5.0 times 10
Yeah.
to the negative 3 numbers? Okay.
Yeah, and the K value too, Gabriella.
Okay. Because I was
Right.
like, I don't know where that came from.
No, it's given, right? All this stuff's given. Everything above here is given.
Okay.
Right. The temperature doesn't really matter. But what does matter is that K value is only good at that temperature. But we're not changing the temperature here. Right. If the reaction is not at equilibrium, which it ain't, which way will the reaction shift and why? Now, because Q is greater than K, let's go back over here. Q is greater than K. See, it's 1002 versus 279. So what you've got to be saying to yourself is, okay, so I know that Q is greater than K. What's Q going to have to do in order to get to K? Remember, if the reaction's not at equilibrium, it wants to get there. I'll say it again. If the reaction's not at equilibrium, it wants to get to equilibrium. So you're looking at the Q expression, and you can see that in order for that to happen, the SO2 and the O2 are going to have to get bigger, and the SO3 is going to have to get smaller. Now that happens simultaneously because the SO3, if it's going in this direction towards the reactants, the SO3 is actually turning into SO2 and O2. So simultaneously, while this is going down, these two values, the SO2 and the O2, are going up. So the SO3 goes down, and the SO2 and the O2 go up at the same time. What that means is the reaction is shifting towards the reactants in order to get to equilibrium. Does anybody have any questions about that? So the reaction shifts towards the reactants. The reaction will tend to a lower Q by decreasing product. Decreasing product or increasing reactants, both of those mean the same thing. Everybody's okay, huh? I find it hard to believe. All right, nobody's saying nothing. See, Zoom is a bit different from a regular classroom. At least I can look around the classroom and I can look for blank faces and people who are have furrowed brows and things. But yours just like looking at, I can't see anything, so I don't know. So I can't really gauge your understanding unless you actually tell me that there's something you're not understanding. Okay. Well, if nobody has any questions, I'll move on to the next part. The next part is about Le Chatelier's principle. If a stress is placed on a reaction at equilibrium, right, that's important. We're talking about a reaction at equilibrium, and we're putting a stress on it. The reaction will shift in the direction to compensate for that stress. So that's the important point about Le Chatelier's principle. We're already at equilibrium, and now we're going to change something in the reaction to make it not at equilibrium. And we're going to investigate what happens to the reaction in order to get it back to equilibrium. So remember that if we have a reaction to equilibrium, any change we make to it will push it out of equilibrium, but then it's going to want to get back to equilibrium again. Right, just think of it like a rubber band. So it's always going to come back to where it was. You can stretch it, but then you let it go, it'll always come back to where it was beginning. So it's the same thing. So here is question C, which is also part of this exam question as well. Consider the above reaction equilibrium. In which direction will the reaction shift when each one of the following stresses are applied to the reaction? Give a short reason for your answer that shows what's happening to Q. And really, I should say, you can only do that for parts 1 and 2 here. Parts 3 and 4 aren't really relevant to Q, but adding SO3 and removing O2, certainly we can talk about that. All right. So these are all the answers. Now, I've got a couple of videos here, or a video that goes through this, I believe. Sorry, this is not letting me. Okay. All right, let me see. Here we go.
I'd like now to talk about and it basically looks like this. So we're going to have 4 SO2s, 4 O2s.
Okay. So this is the story that we're talking about here. Okay, let's say for SO2 plus O2, 2 SO2 plus O2 to give 2 SO3, that's the reaction we're dealing with. And we figure out the value of K, and we do that by saying it's SO3 squared over SO2 squared plus O2. I'm telling you it's at equilibrium. Right, so that's how you know it's at equilibrium, because I'm telling you it is. And then we just count up all these different things, the SO2, the O2, and the SO3, and we come up with a K value of 0.5625. Is everybody okay with that? Does anybody have any questions? Right, that,
So you're just, sorry,
Yeah,
you're
go on.
just counting up the amount of each one and then plugging that in the K.
Yeah.
Okay.
Yeah.
Okay.
Are you okay with the K expression, how I'm getting that?
Yes.
Good, good. So what I'm going to investigate now is what happens if I add a whole bunch of SO3 into the reaction mixture. So what I might do is hook up like a cylinder, gas cylinder of SO3. SO3 is a gas. And then I just pump that into the reaction while it's at equilibrium. So you can see that I've added a bunch of SO3 down here, but the amount of SO2s and O2s has remained the same. But look at the SO3s, see how they've increased? So if I do that, now I can now I don't have a K value anymore, I've got Q. Because the reaction's no longer at equilibrium. I changed it, I added something to it. It's no longer at equilibrium. And I can prove that by counting up everything. And you see I get this value here, 1.266, which isn't 0.5625 anymore. So we know it's not at equilibrium. But further, we also know that the Q value is more than the K value. Right? The Q value is more than the K value. And we've got to say to ourselves, well, what's going to have to happen to this reaction in order to get Q back to K? Well, the Q value is going to have to go down, which means that the SO3 has to go down and the SO2 and the O2 have to go up. So this reaction is going to shift towards the reactants in order to make that happen. So the reactants have to get bigger and the products have to get smaller. Does anybody have any questions?
I have a question.
Yeah.
Just so when you had your equilibrium set up there,
Yeah.
you had a number of 6 SO2s in there. I was just wondering where you got that from.
6 SO2s?
Or SO3, sorry, on top, and then 4 SO2s.
Yeah, these are SO2s here. They're 2s.
Yeah, I see.
And these are 3s down the bottom. So there's 6 of them and 4 of them.
And did you just grab that from the original equation somehow?
What, the numbers? No, I made that up. I made this up. Yeah.
Okay.
I made this up. I just needed a starting point to say what equilibrium was.
I figured as much. Okay.
Yeah. I had to do something. I had to make up something. Yeah, but it came out of my brain. That's where it came from. So we can, then when we change it, we've added something, we get a different Q value, and that Q value is more. So we know that the SO2 and the O2s have to go up and the SO3 has to go down. All right, does anybody have any questions so far about that? Now, from an intuitive point of view, if we don't use math here, right, if we don't use math, here's what we know. If we're adding in a bunch of SO3, then what's going to happen is the reaction's going to shift in such a way that we use up that SO3 that we just added. That means it will go towards the reactant side. Right? I mean, that's just from if we're not talking about math, we're just saying, well, look, I'm adding a bunch of SO3. The reaction's going to say, oh, look, I've got all this extra SO3. What am I going to do with it? I'm just going to turn that into reactants. And that's how it's going to get closer to equilibrium. Now, I've got another one here where I've actually taken some of the O2 out. So that might be if I add something into the reaction mixture that absorbs O2, something like, say, there are plenty of oxides, or there are plenty of other things that absorb oxygen. I can't think of one off the top of my head right now. And you just put that into the container and the oxygen gets absorbed. So we've removed O2 from the reaction mixture essentially. And now we just put in all of these different values. We come up with 1.125 because I've removed oxygen. And you can see again, the reaction is no longer at equilibrium and that Q is greater than K. So again, the reaction is going to have to shift in such a way that Q becomes less than K. So what happens is the reaction goes from the products towards the reactants again. Now, from an intuitive point of view, here's how you can work it. You can say, well, look, I'm removing O2. The reaction's going to want to create more O2 in order to replace the O2 that I took out. And the way it does that is by turning those products back into reactants. But that also has the effect of taking Q down to K. All right, does anybody have any questions about this? All right, well, that's the skinny of it. So that's adding SO3, removing O2. Now, question 3 here, let me get my drawing pad here. Now, this 3 can be one of 4 things. It could be increasing pressure, decreasing pressure, increasing volume, or decreasing volume. Now, this only affects gas molecules. And that's important. Changes to pressure and volume won't affect pure liquids or solids. It'll only affect gases. So let's look at what I'm talking about there. So I think the best thing to use is a piston here to describe what's going on. So let's say I push down on the piston like this. What's going to happen? Actually, let's not put that arrow there. It might be a little bit more confusing. Let's put the arrows here. I'll put 2 arrows here. So I'm pushing down on this piston. What happens to the pressure? Anybody want to tell me what happens if I push down on that piston? What happens to the pressure?
It increases.
It increases, that's right. So pressure will increase. What happens to the volume? If I push down on that, it decreases, that's right. There we go. So if I've got a piston, I think it makes sense. If you've got a gas in there and you push down, the pressure on the gas increases, and then the volume also decreases as we push that piston down. Does anybody have any questions about that? Okay, let's look at the reverse case. We pull up on the piston, and again, we've still got our gas molecules in there. So it should be clear to you that the pressure goes down and the volume goes up. So I think that's a good way of looking at it. Now, what happens from an equilibrium point of view? Well, if we look at the initial reaction, you can see that they're all in the gas phase. So we have 3 molecules on the reactant side in the gas phase and 2 molecules on the product side in the gas phase. And I know that because they have G's next to them. That tells me they're gases. So what's going to happen to a reaction if we decrease the pressure? So decreasing the pressure, what's going to happen is on the reactant side, we have 3 molecules of gas, and on the product side, we have 2 molecules of gas. So when the pressure is decreased, that means the volume's going up. And what's going to happen is we're creating more room in here. So what's going to happen is the reaction's going to compensate by moving to the side that has more gas molecules. So here we have 3 on the reactant side and 2 on the product side. So the reaction will shift towards the reactants in order to take up more of the space in the container, because by decreasing the pressure, we've increased the volume. Does anybody have any questions about that? I hope that makes sense. So when we decrease the pressure, remember the reaction was at equilibrium. The reaction will shift to the side that has more gas molecules. That could be the products, could be the reactants. In this case, it happens to be the reactants. Just count them up. Anything with a G next to it, count it up. That's all you have to do. So if I increase the pressure, let's say it was increasing pressure, then the reverse would be true. It would shift to the side that has fewer gas molecules because there's less space. I'll stop there for a second. Does anybody have any questions? This usually does confuse people, so I really want to be certain that you're understanding what's going on.
So the equilibrium shifts to whatever has less gas molecules.
When we increase the pressure, yes. When we decrease the pressure, the reverse is true. Is that fair enough?
Yeah.
Okay. Does anybody have any questions? So this one usually annoys people, so, you know, come on. Nobody's saying
makes
nothing.
sense to me. Yeah.
Okay, well, that's good. All right. All right. A last one then. All right, let's look at this one. All right, everybody seems to be going well so far. Let's look at the last one. Heating the reaction mixture. All right, let me draw some pictures here for what's going on with heating this reaction mixture. So I'm going to have R and P here. That's reactants and products, okay? Just reactants and products. I'm going to do two different things to it. All right. Anybody know what that's supposed to be, what I'm drawing?
Fire.
It's fire. Thank you. Yes, thank you. It is fire. We're heating it. Okay. What do you think I'm trying to do there on the other one? Any guesses? Kind of like that game Draw Something
Cooling.
a couple of years ago. What's that?
Cooling it in ice.
In ice, that's right. They're ice cubes, folks. All right. So in one situation we're heating, in one situation we're cooling. All right, so we've got two possible ways that the reaction could be set up. So the first one could be R gives P plus heat. We call this exothermic. And R plus heat gives P. And we call this endothermic. Now, I want you to understand the heat that we're talking about here is heat of reaction. It's heat that is either used by the reaction or heat that is given out by the reaction. I'll say it, I'm going to be real clear about this because I really want you to understand this. When I say that I'm heating or cooling the reaction, that doesn't have anything to do with what I'm doing here in this reaction. I mean, this is given as part of the reaction. This heat and this cooling that's done is from the outside. It's not from the reaction itself. All right, I really want you to be clear on that. So going back to this, if you look at the reaction itself, it's got 2SO2 plus O2 gives 2SO3 plus heat. Now, what I'm saying is that when this reaction proceeds towards the product, heat is released. That's what I mean by exothermic, heat out. Exo meaning out, thermo meaning heat. Endo means in, thermo means heat. So heat is coming in. All right, let's talk about exothermic and endothermic reactions as we know them. If you've got a gas grill and you light it up, it gets hot. That reaction is exothermic. That's how you're going to cook your steaks. Right? Is because that reaction of the gas reacting with oxygen is going to be, propane gas or whatever you've got in your tank is reacting with the oxygen to form something and heat. Now, an endothermic process, an example would be, well, there's a couple of examples I can give you. You put an ice cube in your hand. What happens? What do you feel when you put an ice cube in your hand?
Cold.
It's cold. Now, why is that? It's cold because the ice is actually taking energy from you to turn into liquid water. So you'll notice, of course, you have that ice cube in your hand, it melts. It turns into liquid water. But in doing so, it's cold. So exothermic reactions tend to get hot. Endothermic reactions tend to get cold. Another example would be those, you've seen those cold packs, the ones you get a sprained ankle and you break the cold pack, you put, right, that's endothermic as well. So anything that gets cold is endothermic, anything that gets hot is exothermic. Now, question 4 here of this process that we're going through here in the PowerPoint. What we're actually doing is we're doing something else. We're heating or cooling the entire reaction mixture. And whether we're heating or cooling the reaction mixture will determine which way the reaction shifts. But we always know whether the reaction initially was exothermic or endothermic. So here's the thing. Let's say we heat an exothermic reaction like this one here. Okay, so we got heat on the product side of an exothermic. If we heat an exothermic reaction, the reaction will shift towards the reactants. Now here's what I want you to do. If you're heating an exothermic reaction, think of the heat as being a product. So we're adding more product. So the reaction's going to want to use up that product and turn it into reactant. That's how I want you to think about it. Conversely, if I cool the reaction, that means I'm removing the heat, which means the reaction will shift towards the product to create more heat. I'll stop right there. I really want you to understand exactly what I just said. Does anybody have any questions?
Is this talking about exothermic or both?
I'm just really talking about exothermic right now. And if you heat an exothermic process, it'll go towards the reactants. If you cool an exothermic process, it will go towards the reactants. Sorry, products. Sorry, go towards the products.
Could you repeat that again? Sorry.
Sorry. If you heat an exothermic reaction, it'll go towards the reactants. If you cool an exothermic reaction, it'll go towards the products.
Thank you.
Does that make sense? I want to make sure that makes sense, folks. Does anybody have any questions? Now remember, you'll always know if the reaction was exothermic or endothermic. So how will you know? You'll know because you'll be given a reaction that has heat either on the product side or the reactant side. You'll be given that. So you'll always know whether it's exothermic or endothermic. Then you have to figure out what happens when you heat or cool the entire reaction mixture. So you're not just taking heat or cooling from one side, it's the whole thing that you're doing here. So let's say you had an endothermic reaction, you were given that. If you heat an endothermic reaction, it'll go towards the products. If you cool an endothermic reaction, it'll go towards the reactants. So it'll be the reverse of what happened with the exothermic. But my suggestion is always look at the reaction and then treat the heat as either a product or a reactant depending on which side it's on. And if you're adding more heat, it goes to the opposite side. If you take away heat by cooling, it'll go towards that side. I'm going to stop there for a second. I really want that to make sense. I don't want you to think, oh gosh, I'm so confused. I have no idea what he's talking about. If you're in that state, you've got to ask me a question right now. All I'm hearing is crickets. All right. All right. Nobody has anything else, huh? Okay. Fair enough. Let's go take a look at a test question here. And what the test question is. Then I'm going to relate that back to what you're seeing on your test, okay? Or let's see. All tests. Just pulling one up here at random. Download. Okay. So it's question 3 on the test here. And you can see that this is how it's set up. And on your test, it's going to be set up similarly, just split up. And I'll show you what that looks like in a bit. But we consider this reaction, blah, 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 and we've got the reaction here. And then we've got these concentrations, and we also have the K value. So we figure out what Q is by doing, in this case, I wish the student had actually written it out, but it's c squared over a cubed times b squared. And they've just substituted those values in. So c squared is on top, a cubed, and b squared is on the bottom. Is everybody okay with that? Anybody have any questions? So that comes out to be a value for Q of 0.00531. You'll notice the students put a unit here for Q, but you don't really need a unit. You don't need a unit for Q or K. You can include the unit if you want to, but you don't have to.
So the normal formula for Q is c squared over a cubed times b squared?
For this reaction,
Okay.
yeah, just for this reaction, Alyssa, it's going to change depending upon the reaction you've got.
Gotcha.
But it's always products over reactants, and it's always to the power of the coefficient. So in this case, you can see Q is going to be less than K, which makes it not at equilibrium. Does anybody want me to show? Does anybody not understand where that unit's coming from? If you wanted to do a unit,
But we don't have to add a
you don't
unit.
have to do the unit. Did you want me to show? Oh, I can show you how the student got that m to the -3. You interested? If you're not, I'm not going to worry about it.
I think
Okay.
it might confuse me, so that's why I didn't say.
Okay, fair enough. All right. Okay. If anybody else wants to know, I'll answer it. And Gabrielle, you can put your hands over your ears and close your eyes and go la 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 la. All right. So the reaction is not at equilibrium. So the reaction will shift towards the products. Now that's because Q is less than K. So we know that C has to go up. So this top number has to go up in order to make the reaction reach equilibrium, so that Q increases and becomes K. So that's how we know that. Does anybody have any questions about those first two? Okay, these are Le Chatelier questions. So we've got a reaction, it is equilibrium, and we're stressing the reaction out. Kind of like I'm stressing you out right now. So, what do you do when you get stressed? You try and relax, right? That's kind of your way of compensating for the stress that I'm giving you. How you relax, I don't know. Maybe I'll tell you what, I guess some of you might do some deep breathing. We'll say deep breathing. Others might choose another means to relax, but I'm not going to go into that. Okay, so we've got removing A. What happens when we remove A from this reaction? Well, if we look at the, what, I'm going to go ahead and just do the Q expression over here. All right, there's our Q. There's our reaction, and they're all in the gas phase. Okay. So we're removing A. Now, from an intuitive point of view, what we know is that if we remove A, the reaction is going to want to create more A to replace the A that we removed. That means it's going to shift towards the reactant side. The other way of looking at it is that if I'm removing A and the reaction was at equilibrium, so this is not at equilibrium here when we have this, but K is going to be the same thing. Except this is at equilibrium. And this is when we're not at equilibrium. This is after the stress has been applied. So this is before and this is after. You can look at it like that, before and then after. So if we're taking A out, you can see what's going to happen is that the Q value is going to end up being bigger than K. I really want everybody to understand that. If I take A and this is at equilibrium, if this number goes down, I want you to understand that Q is going to go up. That's really what I want you to understand at this point. Is everybody okay with that? So if Q is greater than K, then the reaction's going to have to go towards the reactants in order to get to equilibrium. Because Q has to go down. And the way Q goes down is by increasing the bottom part and decreasing the top part. Increasing the A and B and decreasing the C. Is everybody okay with that? Anybody have any questions? Okay. B, reaction will shift to, let's see, adding B. Let's see what happens when we add B to this.
Shift to the products.
Let's see. Yeah, the reaction will shift towards the products because when we add B, you can see what's going to happen is that adding B will make the Q value less than K because we're increasing the value of the bottom here. So Q would be less than K, which means that it will go towards the, so Q is greater than K, that means the reaction goes towards Magic Select. What are you doing? I didn't want to do that. Come on. I need to get out of this somehow. Here we go. That's better. Right. If Q is greater than K, then the reaction shifts towards, all right, let's not do that. Shifts to reactants. If Q is less than K, the reaction shifts towards the products. So adding B will shift it towards the products. Anybody have any questions? What happens if we increase pressure? So what I'm going to do here, let me move this. Okay. Is I'll show a picture of a piston here. So we're increasing the pressure, which means that the pressure is increasing and the volume is going down. So if we're increasing the pressure, then the reaction will shift towards the products because it has less gas molecules. So we're going from 5 to 2. Let's see how we count that up. So on the reactant side, just look at here with the gases, we've got 3 plus 2 is 5. And on the product side, we've got 2. We're increasing pressure, so the reaction will go towards the side that has fewer gas molecules, which is going to be on the product side, 5 to 2. Does anybody have any questions? Okay, the last one here, heating the reaction mixture. All right, so this is the reaction. We're going to heat it, and since it's exothermic, because we know heat is on the product side, then the reaction is going to shift towards the reactant side. It's going to use up the heat that we're adding and turn everything into reactants. So the shift will be to the reactants because we're adding heat, and heat is also a product. Does anybody have any questions? Okay. Let's go take a look at the test questions that relate to this. Remember, these don't change, right? I mean, when you take this quiz and then you take the test, it's going to be the same. See, they're copies. It says it's a copy. It's a copy. All right, here we go. So for the following reaction, calculate the value of Q. Notice I don't give you K because you don't need it here. Does anybody have any questions about how we would do that? Number 12? You're all okay with that? I mean, I'll just go ahead and just give you the rundown on it very quickly.
It'd be 0.65 to the fourth power divided by 0.16 and times 0.78 to the second power.
That's right. Yep, that's right. That's how you set it up. Yeah, so I'll just go ahead and do that. Q equals, it'll be C to the fourth over A times B squared. So we don't have to put any units in, but I can tell you the unit. Does anybody know what the unit's going to be? Just out of curiosity. Let's say that let's say they were all molar. I really should have concentration units in them, but let's say they're all big M. Can anybody tell me what they think the unit of Q would be if you had to include it?
Just M.
Just M, that's right. It's like magic, isn't it, Kyle? I wonder how he got that. Well, it would be like this. Be M to the fourth. Gabriella, close your ears. Over M cubed. And that would give M 4 minus 3 is 1. That's if you had to include a unit. All right. But you don't have to include a unit. Question 13. A reaction A to B is found to have a Q value greater than K. Which way will the reaction shift? Well, I'm going to leave it to you to figure that one out. We've talked about that. If you have trouble with that, you should get back to me. Well, I guess I'll look at it here. All right. So Q is greater than K. So the reaction will shift to a lower Q and bring it closer to K. Well, I think it helps for this one to show what the Q expression looks like. Okay. So let's look at the first one here. The reaction will shift right. Well, let's see. Will the reaction shift right? So Q is going to be greater than K, and that's what we're told here. That means that...
I think it's the second one.
You think it's the second one? Okay. The reaction will shift to lower Q, bring it closer to K. B will go up, and A will go down. You think that's the right answer, huh?
Q is greater, so
Q is greater. So Q has to go down, which means that A has to go up and B has to go down.
My bad. I thought I said last time.
All right. So will the reaction shift right or left? No, the reaction is going to have to shift left. Okay. So we're going to find that one. The reaction has to shift left to lower Q. A will go, so it's this one here, isn't it?
I think so.
Yeah, so reaction will shift left to lower Q, bring it close to K. A will go up and B will go down. So you have to figure out which one it is of those. All right. For that one, it was the one I just pointed out. Okay, question 14. Consider a reaction to be at equilibrium here. Which way will the reaction shift if B is removed? All right, does anybody want to say? Reactions at equilibrium, which way will it go if B is removed? Reactants or products or not? No shift?
Reactants.
Reactants. Why are you saying that, Kyle?
Because it has a lack of reactants in this point, and I'd say an excess of products.
All right, so we've taken out B. We need to make more B in order to bring it back to equilibrium, in order to remove that stress. So the reaction will shift towards the reactants for that reason. All right, anybody got any questions about that? All right, which way will the reaction go if we add more A? Any thoughts? Products, reactants, or no shift?
Let's shift to products.
Products, that's right, because we need to use up the A that we're adding. And if we do that, we add more A, it'll turn into C and D, more C and D, so it'll go towards the products. Any questions? Okay. In which direction will the reaction shift if the reaction volume is increased? Now remember what we're doing if we're increasing volume. We've got our piston, increasing volume. So the pressure is going down, the volume's going up. Increasing volume. Okay, all right. Now, which way will the reaction shift in this case? It will not shift towards the products or shift towards the reactants.
Where did it not shift?
No, it will definitely shift.
Oh.
And which way is it going to shift, though? Is it going to shift towards the reactants or the products?
Oh, I was looking at the one beforehand. Sorry.
No.
That was the reason why.
Are we still talking about increasing the pressure?
Oh, sorry.
You scroll down a little bit.
I'm sorry. I scrolled too far. I apologize for that. Here we go. We are increasing the volume.
Or increasing the volume?
Yeah. Yeah, it makes it a bit easier if I got the question actually there.
Yeah, I didn't read the whole thing. That was my reason.
Sorry about that. All right, which way is the reaction going to go? We are increasing the volume.
Towards the products.
Now, why do you say that?
It has more molecules.
Oh, what's important here if we're talking about pressure and volume, though? What kind of molecules?
Gas.
Gas molecules. How many gas molecules do we have on the left?
Yeah, there's more.
7. How many on the product side?
5.
5, not 8. Now
No.
the 3 there is 3D is a solid, right? Pressures and volumes won't affect the solid. The solid's just going to sit there and look at you. But pressure and volume do affect the gases. That's why I was real clear in the explanation here when I was talking about this earlier. This only talks about gas molecules. Oh, it's tricky, isn't it?
It'll shift it to the reactants.
Yeah, volume's increased. It'll shift towards the side with more gas molecules, which means it will shift towards the reactant side. 7 versus 5. Does anybody have any questions? Okay, question 17. In which direction will the reaction shift if the reaction is cooled? Okay, anybody want to tell me? If it's cooled, which way? No, if it's cooled, it's going to go towards the reactant. The reason I say that is because heat here is on the reactant side, making it endothermic, which means that if I remove heat by cooling it, I'm taking heat away here. So the reaction's going to want to create more heat by moving to the reactant side. So think of the heat as being a product or reactant, in this case, a reactant. If I take out the reactant by cooling, then the reaction will shift towards that side. Does anybody have any questions?
So it's shifting toward the reactants for that one?
That's right, Gabriella.
Okay.
Are you okay with Y?
Yeah.
Okay. Does anybody have any questions about that?
I do.
Yeah.
If the heat is on the product side and the heat is, or if the reaction is cooled and it was on the product side, then the shift would once again still go towards reactant, or would it go towards product?
It'd go towards the products if that were the case, because you'd be
Okay.
removing a product, which means the reaction would want to create more products to compensate for that, for you taking out the product. Here, the reaction is taking, in this example, the reaction is compensating by creating more heat. You with me?
Yes, I'm taking notes on it.
Okay. Does anybody else have any questions about this? All right, let me re-roll here, and we'll look at some different examples of the same questions. Well, I think we're okay with this one. As you can see, it's going to change depending on what we're talking about in 13. Let's just focus on the Le Chatelier's principle here. Okay. Which direction will the reaction shift if more C is added? Number 14.
It'll shift towards the reactants.
All right, because we want to use up the C that we've added. So it will shift towards the reactants to use up that C. All right, 15. If more A is added, which way will the reaction shift?
It'll shift towards the products.
Right, shift towards, that's right, to use up the A, that's right. Okay. All right, which way will the reaction shift if the pressure is increased for this one?
It'll shift towards the products.
Now, why do you say that?
As you increase pressure, the side that has, it'll shift towards the one that has the least gas molecules.
Okay, now that's true. It will shift towards the one that has the least gas molecules. How many gas molecules are on each side?
7 and 5 respectively.
No, it's not 7 and 5. Take a look.
7 and 7.
7 and 7.
And there's heat on the product side.
Right, but that doesn't, the heat doesn't affect anything here. So since we're not changing the molecules on either side, it won't shift. It won't shift. It will not shift. That's the answer there. Any questions? All right, the last one here. Well, it's going to be the same as what we had earlier. Reaction's cooled. I want to know the heat is on the product side here. I think it was different from the last one. It will shift towards the products if we cool the reaction. Any questions?
No.
All right. So there you go. Well, you know what you need to do to practice these. You've got your homework, your extra credit quizzes for this, and then you've also got the quiz questions here in the ungraded copy of test 1. I would practice those, make sure you understand how to do them all under any circumstance by doing them again and again, and you should be good. Right, if anybody has any questions, you can contact me by email or on my cell phone. You know where my cell phone is. It's in the syllabus. I do have people calling me. It's cool.
I have a quick question, but not regarding the information, because I get that it's just for the extra credit quizzes.
Yeah.
So for those quizzes, since they're worth extra credit, do we only get one attempt for those and that's it, or do we get to take those multiple times?
Two attempts.
2 attempts. Okay.
No, but you have to do the practice quiz first to open the credit quiz. You need 80% on the practice quiz to get to the credit quiz, and then you get 2 attempts at it. And it takes the higher of those 2 grades, Gabriella.
Okay, that's what I was wondering. Thank you.
All right. Anybody have any other questions? All right. See you all later.
Bye.
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 If anybody wants to hang around, they're more than welcome to hang around and ask questions if need be.
I do have one thing to say.
Yeah.
This doesn't really relate to the course material. It just relates to the Zoom call.
Yeah.
If nobody's speaking, I just have a suggestion. You can have people in the participants area. There's a yes, no, raise hand. Those are some those are some things they can press. So if like nobody's responding, you can get them to answer through that.
Okay. Yeah. Now, I wonder if I do that. I might have to do that through the chat box, probably, right? I have to have the chat box open in order to
I don't think you need the chat box open. You just need the
All right.
participants open.
Oh, okay.
And you can also reset the.
Oh, okay. Here. All right. Yeah. All right. Okay. Yeah. All right. I might. Yeah. Okay, Jack. I'll try that next time. Okay.
Mm-hmm.
I wasn't here. I wasn't able to make a class on Tuesday, so I was looking for the Zoom meeting for that day, but I couldn't find it.
You mean on the Tuesday Zoom meeting? I didn't put it.
Yeah.
Okay. I'll look. I'll try and put it up I'll try and put it up now if it's not there. Okay.
Okay. Thanks.
Okay. No
Have a
worries.
good weekend.
You too. I'll see you later. Berkeley, you all right?
Yeah, I'm good.
Okay. All right. I'll see you later.
All right. Bye.